G'day everybody. I now would like to introduce my dad, Derry Doyle, otherwise known as the Prof. Thank you to somebody, a good friend of ours called Jegsy, who used to love calling my dad the Prof. It will be fair to say that he grew up in some pretty tough environments back in the UK, in Wigan, and things were not always easy for Dad as a kid. So the fact that he's been able to go on and become a scientist, a metallurgist, and so many other things, lots of letters after his name, we call him the Prof. So this is a full circle moment. You're about to experience life in metallurgy. So please give Dad a warm welcome to the Prof.
Thank you, Emma, for that very kind introduction. The title, Life in Metallurgy and its Application in Metal Cutting. So two themes here, metallurgy, metal cutting. Interestingly, metallurgy, metallurgy, we say things a little bit differently. Let me tell you a little story. When I was in Minneapolis with a great friend of mine, Professor Ramalingam, we were having lunch, and as I moved through the cafeteria, this lovely lady said to me, would I like some tomato with my lunch? And I was being a little bit smart and said to her, well, I'm not sure, but I wouldn't mind some tomato. And she looked at me and said, well, I suppose, would you like some potato as well? So she got me, and that was just lovely. I've never forgotten that one. So metallurgy, metallurgy. And if we have any other problems, please stop me and ask. Now, let's look at the background for our conversations for the next hour or so. The background, as Emma said, I have a background from the north of England, in particular Wigan, and...
Hang on, let's do that bit again. Just go through the structure and then go into the background.
Oh, okay. Go through.
Tell them what you're going to tell them.
Go down and then go.
And then go background.
Okay. The structure of... Okay, the structure for this morning then is the background. For me, we're going to look at Metal Cutting 101. What do you find in the textbook? What does it say about cutting metals? And we're going to take something a little bit different, a little bit original, that we've got some sort of reputation for, and that is machining inside a scanning electron microscope, meaning we can look at the dynamics of chip formation at very high, 10,000 times magnification. And then how do we look at making coatings, PVD, physical vapor deposition, making coatings from the vapor state, and then we take all that into the real world, into Sutton Tools. So now the background, and that's a nice shot of the family. That's obviously Emma and I in current times, but the one on the right is myself with Emma when we were in Cambridge. And would you believe we were doing metal cutting even in Cambridge? And it was fantastic. And it was fantastic having little Emma in store, and she's obviously enjoying it. Now, my academic background, I did my degrees in metallurgy at UMIST, University of Manchester Institute of Science and Technology. What a brand name. Doesn't exist anymore. It's now just the University of Manchester. Big mistake in my view. Now, at UMIST I did a BSc and PhD in metallurgy. My career from there was in defence in Australia, the Defence Science and Technology Organisation, for about 20 years as a research scientist. And then in 1988, I left defence and went into, joined Sutton Tools, and we formed a company called Surface Technology Coatings, which still exists today. And I also was a professor at Swinburne University of Technology and the Royal Melbourne Institute of Technology in Melbourne, 2009, 2019. So that's roughly my career, one academic and two of the real world application. So I'm a metallurgist, so it is a metallurgical theme from what I've got to say. In manufacturing, I have been involved in metal cutting. That's what's interested me. I've even done that in the universities, in the Commonwealth Scientific Organisation, in Cambridge, and in the real world. So we've covered everything. So well, let's start at the beginning. And please, hands up or contribute if I'm missing something or something that you experience. But this is a typical sort of image, isn't it, that you might find in a textbook on metal cutting. Now, here we've got a cutting tool. There'd be a planing operation. We've got the workpiece and the chip. So they're the three things. The workpiece for us at the moment will be mild steel or copper or brass. The cutting tool, from where we are going, we're mainly talking about high-speed steel or tungsten carbide cobalt. So carbides, high-speed steel. Remember, as far as that cutting tool is concerned, we started off, didn't we, in the 1700s, 1800s, with plain carbon steels, tools, and they're very hard. And if you're a heat treater, do you remember what your heat treatment is for a plain carbon steel? You harden at about 800 to 900. You quench, and then you temper about 200. Okay. And your cutting speeds, 10, 20 feet a minute. Not very much, but pretty good if you're in 1850. In that late 1800s, Americans played I got in trouble once for giving a talk and saying it was all Americans, and I got told off because the English also did a lot in heat treatment. Mush it, I don't know if you heard the term, mush it steel. But I think Taylor and White, is it the Bethlehem Steel Company? They're the ones, I think, that made tremendous progress with what we call high-speed steel, okay? 1841, 18 tungsten, 4 chromium, 1 carbon. And what I think is clever about Taylor and White, and we're talking about 1900, 1910, what they did was take the steel and they hardened it not at 900, which everybody had been doing for 100 years. They went up to 1200. Ah. And then when they tempered it, they didn't temper it at 150, 200. They were tempered at 450. So those subtle, they didn't happen overnight, but those changes are tremendously important. And that high-speed steel, of course, is still one of our main tool steels today. And what's important about it is its ability to withstand the heat as that chip moves. Does it slide? Okay, that's still very, very controversial. As that chip goes up the tools, and it'll start generating enormous heat. So that tool has to withstand the heat of sliding friction. Tungsten carbide cobalt. that's a sintering operation. That'll withstand about 600. Of course, high-speed steel, that's going to withstand about 450, 500 degrees centigrade. Okay. What else? I'll just say one thing, but you'll see it more. The intense deformation along there is important, and it's something that I've written papers on, and taken a long time for metallurgists to really understand what's going on. But let me just make one point. As the workpiece is coming along, there's an enormous normal force. If we're talking friction, that's friction. Well, that's an enormous force along there, and it's got to move up. And then it's got to move. It's not seeing any oxygen, and that's important to recognize at this point. So when you're throwing your lubricants and oils at that area, you know, you're lucky if you can get in here. That's why you use pressure. Okay. Now, what does the metallurgist do? He or she comes along and starts cutting it up and look at the microstructure. We love microstructure, okay? And we'll have a look at that. We'll take a standard look at microstructure. And what do we learn from that? A bit of 0.1% carbon steel, a nice bit of mild steel. And I like this one. We were very, very good metallurgists, by the way, in the research labs that I worked at. We had a super metallurgical laboratory. And you see what we were saying about the deformation in the chip? You can see the shear, what we call the shear plane. And this, of course, is, anybody know what the dark bits are?
Porosity. Porosity.
I'm sorry, I'm partially deaf.
Porosity.
No, I'm glad we picked that. No. It's perlite. It's a mixture of iron carbide and ferrite and iron. So, thank you. It's not porosity. This is a real quality steel. So that's a good image of the chip formation. You can see a little bit of deformation as that chip was trying to move up the rake face of the cutting tool. Now, quite often, that will break down and we'll see what's called a built-up edge, this thing here. And we're going to see a lot more. Yeah, next one. Now, this is metal cutting in brass, you know, 70-30 copper zinc alloy. Okay. And what's interesting when you look at brass is, we've etched this in ferric chloride, which brings up the deformation, this dark etching. And look how thick the chip is. So actually, a nice soft bit of brass, it can be quite tricky if you don't get your geometry right, okay? And what is also interesting about brass is look at the deformation in the cut. So this is the cutter going that way or the chip going this. Look at the deformation under the surface. So when you machine things, you actually deform the surface that you're cutting. And if you're making critical components, you've got to recognize that there's residual stress in that surface. And this is the surface damage. In fact, what we do in machining often is rough cut, and then finish machine. Whoop, sorry. Finish machine through this, and we'll see. I think that's classic metallurgy. here is machining in brass, but it's machining through a heavily deformed layer. And look at the chip. Quite different in its, and the surface finish is quite different. Okay, and the last one is titanium 6 aluminium 4 vanadium. Again, we were defense, so aerospace industry. And you see segmental chip formation, not continuous chip. Quite a different structure. Okay, that's a classic bit of metallurgy. Now, so far we've looked at static images because that's what we do as metallurgists. Now, what about looking at the dynamics of chip formation? How do we do that? We machine inside a scanning electron microscope. Just stop it for a second, Em. Again, can I ask, has anybody seen this on Doodle or what I'm about to show you? Machining, metal cutting inside a scanning electron microscope. And we'll be talking about Sutton Tools shortly. And I was speaking to Peter Sutton 2 weeks ago, and he said, "Oh, Derry, I've got it." And he's a bit of a podcast fan, and he actually got the image and put it up. And he didn't know I'd done it, which is interesting. By the way, this work was done in the early 1970s. It's a long time ago. And notice, Materials Research Laboratories, the Australian map, what's missing? 1975, what's missing? Derry Doyle. We didn't put our names on anything. It's weird, you wouldn't do that today. You'd be wanting money for this. In fact, I'm not sure which American company, whether it was Boeing or something, but they've got this. And they've used it. And I was giving a talk going, hey, they didn't ask for my permission. So I showed a bit of their stuff as well. So I passed it. Okay. So chip formation, don't worry about that for a minute. Let's just go. Yep. And here we are. We've got our cutting tool, high-speed steel. This is the state. It's a disc about 50 millimeters, 50 centimeters. Now this all goes inside a scanning electron microscope. And there's the drive of driving the disc against that cutting tool. There's, God bless her, Veronica. She said, well, you know, we've shown this video all over the world. She would want a different dress. I mean, you know. Okay, and that's a very old scanning microscope. So don't forget, we can look at the tip of the cutting tool at 10,000 times magnification. Okay, so let's start. Mild steel, high-speed steel. And that's, I'm sorry about that, that's a little bit of dust. There's the carbides, and we're cutting nicely, getting a bit thicker now, and then we've cut into the built-up edge. Okay, notice this actually becomes the cutting edge, and it's cutting itself. There's an inclusion, and then that will start to go. So that'll affect your surface finish, but the cutting edges do no cutting.
Is it like that on any material?
Sorry?
Is it like that on every material?
No. Okay. So there we've taken high-speed steel and we've been cutting a bit of mild steel. But what we're going to do next is coat the cutting tool with a PVD. What does PVD stand for? Physical vapor deposition. PVD. Physical vapor deposition. The PVD revolution, that's about, for me in Australia, about 1980, where we start to look at putting coatings on cutting tools. And given that in Australia, we've been looking at friction, at those mild steel pitches, we were looking at modifying the friction in metal cutting and improving the performance of our cutting tools. Because that's what we're here today, is about performance of cutting tools. Okay. We'll say more about the coating in a minute. Wow. Okay. I know it's not yellow, it's the electrons are not colored. All right, so you've got to take that that's yellow. And now just look at this. And what I love, I love the image of this anyway, but look at the nose radius on the cutting tool. Still, it's acting as almost a little mini built-up edge, which must affect your surface finish. But it's hard not to start. If you have an infinitely sharp tool, it's not going to stand because it'll break. It's great going to work and doing things like this when it actually works.
What year was that footage?
75. 1970s, late 1970s, yeah. I had a great little team, by the way, doing this. I was, wow, this is an electroslag refined steel. We were defense, remember. Very different. By the way, this is the uncoated one, isn't it?
Yep.
Yeah. Oh boy, it's struggling. Look, the forces are very high. This is done very slowly. Electroslag refined steel. We've refined the steel. We're going to make gun barrels out of this stuff. Okay, so you want quality steel. But in that quality, in removing the inclusions out of the steel, it's a lot more difficult to machine. So this is an uncoated tool, plain. Look at the shear plane and the cracks that are forming. Very difficult. By the way, this is not on Google. You'll see the first bit, but not this stuff. This is buried in the archives. Okay, so really what we want to know now is, well, if we coat the tool, the cutting tool, with titanium nitride, does that change things? So electroslag refined steel, titanium nitride. Again, look at that. Movement up there. This is in vacuum, by the way. There's no oxygen here. Moving beautifully. It'll still crack a little bit. That's why this was a revolution in metal cutting. Again, you see that nose radius effect. You won't find that in the textbook. Yeah, and it's sliding, it's moving, there's a crack, off it goes. Right, okay, next one, last one. Stainless steel, austenitic stainless steel. Uncoated, huh. That's about as bad. It's another example of a relatively soft steel. They're not easy to machine. In fact, it wants to get round the cutting tool rather than go up the rake face. So your question about the different material, perfect, isn't it? And now titanium nitride. If you put titanium nitride on, you start to cut the stainless steel quite nicely. Yeah. Stainless steel, where was that invented, developed? Anybody? Stainless steel.
Germany?
Germany?
Yeah. Italy?
I'm English, come on. England, about 1920s. And also we're talking about 18-8 stainless, 18 chrome, 8 nickel. And so it must have been some very clever research they were doing in, which town would it be in England? Sheffield. You know, the knives and forks, they're generally stamped with Sheffield on. And you know what? They were making gun barrels, okay? They were experimenting with chromium. And one day they were increasing the amount of chromium that was in their steel, and they got over 12%. And it was lousy gun barrels. So they threw it out. Now it rains a lot in Sheffield, okay? And 6 months later, not the man who's credited with discovering, he got the credit, but it was his technician came in and said, "Hey, Harold, that steel we were working on," I'm trying to do the Yorkshire accent, I'm not very good at it. Everything else it's not rusty. They'd thrown it out, and it was as bright as 6 months ago. And that was the discovery of austenitic stainless steel. Okay, you've only gone 2 hours. I'm 28 hours from bloody flying from Melbourne to. Okay, this one. Oh, that's right. Remember when I did that work when I got to Melbourne and we under-hardened the high-speed steel? We didn't know why it worked, but we know. Now we know a lot more about this thing, this built-up edge. So when the tool starts to wear, because we've under-hardened it, it creates this prominent. So it wasn't wearing out. So the tools were lasting a hell of a lot. For this particular application, it was what we call a spheroidized low-carbon steel. Very soft, very ductile, okay? So that actually worked for us, okay? This PVD, and I've just mentioned titanium nitride. So has everybody heard of titanium nitride? Yeah? Yeah, okay. By the way, what sort of material is titanium nitride? Anybody? It's not a metal, not a plastic, it's a ceramic. What's the definition of a ceramic? A metal and a non-metal. Titanium nitrogen. We're putting two together. Ceramic, aluminium oxide, tungsten carbide. These are ceramics, metals and non-metals. They're hard to manufacture, in other words, the high temperatures, but they're very hard. So that's why we want as on our cutting tools. We want hardness at high temperature. Okay. So how do we manufacture a ceramic from a vapor state? Let's look at that. Okay. So here's our drills in the holders that's going to go into a chamber. And this is the machine that we purchased for $1 million in 1988. That's the chamber. Drops down, pulls out, and you load. We're going to look inside the chamber so we know what's happening. By the way, we've still got that machine operating. Here we are. It's in a vacuum, rotary pump and diffusion pump. So it's a vacuum system. And what we do is we generate electrons, and with the electrons we heat up the cutting tools on those spindles. And there's about a dozen spindles in that chamber. Okay. Then we focus the electrons down onto a copper ring down here. And what that does, we let in argon, and it creates a plasma, an energetic argon ions. And those argon ions start hitting the tools and cleaning them atomically. So we want clean surfaces. And then the last one, we focus the electron beam onto titanium, and we melt that, and we let in nitrogen, a reactive gas. And that's 2 microns. Look how dense and uniform that coating is. So notice what we've done there is it's all about creating a metal vapor, PVD, physical vapor deposition. It's about creating a metal vapor and then a reactive gas to bring the two together. Now, you're limited to maybe 2 or 3 microns, because if it goes any bigger than that, it just won't bond to the surface. So you've got limited to the thickness. Now, there are other ways. By the way, I'm sorry to say, that was a Swiss machine. I remember meeting a guy called Peter, he's probably dead, a guy called Peter Flood from Iron Bond or Multi-Arc, which is the American system. It's another story. Shut up, Derry.
This is my favourite.
Look at this.
I love this one.
You can see the way you'd use it with the great system. You use an electric arc, and it's blasting out this intense vapor of titanium, and that's there you can see the tools being coated in the arc process. Now, if I can just, again, hold up for a second. You see, when we're evaporating titanium, now let's say so titanium nitride, but now we've also got titanium aluminium nitride, made it a bit harder. Titanium, well, it's not so easy in an evaporative system, is it? How are we going to melt titanium, melt aluminium? The arc system is brilliant. There you can run the arc on a cathode with titanium and aluminium. Okay. Right. Only trouble is the intensity of the arc gives you lots of macroparticles. That's the bit that I don't like. And when you look at the evaporative systems, it's much smoother. So in tapping, I think I prefer that. But if you're milling, and that's great. And the last thing that the arc can do, we just stop this for a second. and I think this is the new generation of coatings that we'll see, is there's the steel. This is chrome nitride. Now look at this. And by the way, 100 nanometers. We've got chrome nitride, titanium, aluminum nitride. Multi-layers. So I think the possibilities for this are really, I'm too old now. I wish I was still doing it because there's fabulous technology here. Okay, fine. We're at now. Let's go into the real world. Okay, that's by the way, in all that. By the way, I spent 2 years in Cambridge. Cambridge, you know, brilliant. Enjoyed every minute of it. Worked with a guy who's now in San Francisco, Greg Horne, fabulous guy. Anyway, and we used transparent cutting tools. Okay, we could actually see. Oh, incredible. Now, Sutton Tools, a family-owned business, 4th generation. That's unusual. 4th generation Sutton Tools. This one. I noticed, by the way, they call themselves Sutton now, not Sutton Tools. When I was there, it was Sutton Tools. Jim, that sort of, it's a family business. Started in 1917. And I worked, Jim Sutton, great mate. We used to play golf together. Jim kept saying, Gary, we've got to get you into the real world, get you out of that research stuff. And bloody hell, Jim, you should have left me, for God's sake, eh? The real world's great, but it's got challenges. You've got lawyers and all sorts of problems, right? We started a little company called Surface Technology Coatings in 1988. Right. I wasn't the general manager. Complicated. 2 years later, I was made general manager. And I was dealing with lawyers at 2 o'clock in the morning. Why? Because we were in receivership. Okay? Do you know what the interest rates were in 1990? Have a guess. Anybody?
18%.
18. You try running businesses on borrowings on that. Okay. So it was a challenge. We got through all that. I was general manager for the next 15 years of this small section. And in that, but American, Abar Epson, by the way. This is the vacuum heat treatment furnaces. That was 2 weeks ago, me. That was about 10 years ago. Me being a fool, dressed as Rod Stewart. And just a point there, by the way, by the way, I was general manager and I was a professor. That's how this damn professor thing comes up in one of the technical universities. So I combined two things. It's complicated how that happened, but it did. Okay. And that day I'd given my last lecture to 200 engineering students. And I went in dressed as Rod Stewart. Now, I'm not, I was sort of lecturer that expects people to listen. If students don't listen, I'll get out, you know. So to say they were surprised when I walked in dressed like that was an understatement. But what was good about it, I meant to go in just to get, but I did a 2-hour lecture dressed as that. And at the end, I got a standing ovation. I mean, it was Mr. Chips' experience. That's the movie, Mr. Chips. It was fabulous. I really enjoyed that. Okay, so Sutton Tools. This is Peter Sutton. You can see the next generation coming through. A good mate of mine. This is the research environment. And what interests me now is when Jim, by the way, Jim and Bill, they always say I have 2 brothers running this show. There's Australia, by the way. It's a long way. There we are, that's the head office. But you can see the offices all around the world now. Lovely, about 500. Hey, that's good, isn't it? That's the machine we bought in 1988, yes. and Sergey worked with me about 1991, and this guy did the heat treatment. Okay, they were just about, both of them about to retire. So that, and again, that was a couple of weeks ago. It was nice to catch up with them. But that machine, look at that. It's doing coatings as well as it when we first bought it. The classic environment. A lot of anchor machines, Australian, which I think is #1 now. So do we have a takeaway? I'd be interested in your comments. But for me, it was gaining metallurgical insight into our friction and microstructure, friction in coatings, the microstructure, the way we change microstructure to affect the performance. So happy to engage on that. And your comments on what you've seen. Thank you.
So big round of applause. We've probably got time for one insight and one question, and then I'll go over to Steve. Anyone? Yeah, thanks. Nick?
So what is the difference between metallurgy and material sciences?
It's a lot of plastic in material sciences. That's a quick answer. Yeah. I'm not so good on I know a bit about plastics, but when I did metallurgy in 1963-60, no plastics. Metals and ceramics. Good question. But I don't know, today you won't find metallurgy, but you'll find material science. And then they water down the metallurgy. We did 3 years of metallurgy. And it's a great question, because the number of times I have been fighting in heat treatment with bloody Europeans. You're making blocks of, die blocks for plastic molding or something. Okay. And bloody thing cracks in America. And this happened to me. And we've got to figure out it's your heat treatment. Because the heat treater is the last one to deal with that block of steel. And I've had to deal with, I remember there was an Italian. I go over to Europe. I've got this Italian. He doesn't know anything about metallurgy. He's using words that are wrong, So, if you either know your metallurgy or you don't. If you don't, shut up.
An insight? Someone?
I just thought it was interesting to see that zoomed in build up, because we all know we get build up on tools.
Yeah.
And seeing it zoomed in like that really shows how much build up you can get on causing the surface finishes to be rough.
And Dad, James is the gun guy.
Oh,
Gun barrels and guns.
so are you using electroslug refined steels? Do you know?
Do you want that?
Are you using electroslug refined
We're
using
using like 17.4 stainless.
Oh, okay. Yeah, righto.
Is mostly what we're using right now.
Yeah.
So I got a question. When you were doing your tests on that, when you were showing it magnified, the
To 10,000 times.
yeah. So did you use your surface footage and your chip per tooth figures to control your edge? Because you can control the buildup on the edge of a tool by how fast you're taking it in and out of the material.
You're right. I think the value of this sort of stuff is actually getting an insight into what the hell the workpiece is doing, and now adapt your geometry to suit that. Because if you don't know what's going on, it's very difficult to adapt, isn't it? You're flying blind. But that gives you real insight. Even the static images they're good, but they're limited. It was just fantastic doing that. Yeah, and we had a great engineering shop in our research labs, and I worked with the guy there, and we did fine grinding, and it was 20 years. I loved it, and then I get in the real world. You know, you're dealing with lawyers at 2 o'clock in the morning and people who don't bloody know what metallurgy.
Positive. Coach James, come back. The positive is going to be Steve. Steve's got a few things to say.
Well, we just want to thank you for taking the time, flying all the way over here, and then taking the time to enlighten us on some of this. I mean, a lot of us work with metals every day, but as far as digging in and seeing your insight, we truly appreciate it. So just a small token of our appreciation for taking the time, and just everyone stand up, give him another round of applause. Thank you so much.
And,
Truly appreciate it.
Thank you.
and it's Dad's 81 tomorrow.
Happy birthday.
So happy birthday for tomorrow. Make sure wish him a happy birthday if you see him. He'll be around. We fly out Thursday morning.